sections. (4.2) and 4.3. Determinants and operations. First, definition. Given a matrix A represented by a matrix A with size 2 by 2 represented by A11, A12, A21, and A22. We define the determinant of A determinant of A as the number computed from the entries of the matrix in the next way. A11 times A22 minus A21 times A12. In other words, this number called the determinant of a matrix of size 2 by 2 is computed by multiplying this diagonal, this times this, minus this, the multiplication of the numbers in this diagonal. This times this, minus this times this. Example. If we have the matrix A given by 1, 5, 3, 2, then the determinant of A is equal to 1 times 2, this times this, minus 3 times 5. And this is 2 minus 15, equal to negative 13 in this case. So the determinant is a number, it's a real number. Now, part of the purpose of this video or these two sections is that we can define a determinant for a matrix for any square matrix with size n by n. I want to point out that this definition for a determinant, we start with a definition of a 2 by 2 matrix. This definition is for a 2 by 2 matrix. This has size 2 by 2. The determinants here, they're going to be defined only for square matrices. Remember, a square matrix is when it has the same number of rows as columns. So first we start with a matrix with size 2 by 2, and then I'm going to define so that you can get used to how to compute the determinant. I'm going to define how to compute it for a matrix with size 3 by 3. I want to point out that the definition, I'm going to be using here the definition to compute the determinants. If some of you already have experience with determinants and you know other methods to compute those determinants, no problem. As long as you are right, you're doing the right you're having the right answer, no problem as to how you compute them. But determinant of a 3 by 3 matrix. Now, if we have the matrix A represented by A11, A12, A13, here A21, A22, and A23, here A31, A32, and here A33. Then the determinant of A is given by, focus on the first row. I'm going to use first the first element, A11, in the first row. It's going to be A11 times the determinant of the matrix. Notice, since I have chosen the row 1, the element in the row 1, column 1, this one here. Now, I'm going to eliminate, well, imagine that we eliminate the row 1 and the column 1. If we do that, I eliminate row 1 and column 1. So what is left? That matrix, you see, A22, A23, A32, and A33. So this is what I have to put here. So A22, A23, A32, and A33. Minus. Now, the second element in the first row is the element A12. So you put A12 times, repeat the process as before. This entry is in the row 1, column 2. So imagine that you eliminate row 1 and column 2. What is left? A matrix with size 2 by 2, A21, A23, A31, and A33. Yeah, I eliminate this row and this column. So what is left? A21, A23, A31, and A33. Then plus the next element in the row 1, A13. And again, this entry is in the row 1, column 3. So now eliminate the row 1 and the column 3. Row 1, column 3. What is left? A21, A22, A31, and A32. Oh, I'm sorry. I think I forgot to mention what is the meaning for this. This is the determinant. Another way to represent the determinant is like you put the matrix between bars. For example, A11, A12, and A21, and A22. So the determinant of A is equal to this and can be represented by this form as well. You write the matrix and put the elements of the matrix or the matrix between bars. So this means determinant. Okay, it's the same. So this determinant. So this is the definition for to compute the determinant of a matrix with size 3 by 3. You will understand why this is the definition later, because we're going to define later on how to compute the determinant for a matrix with size n by n. But by now, let's get used to this one. So, for example, example, given the matrix A 1 0 negative 1 5 2 3 negative 2 6 4, find the determinant of A. So the solution is, follow the definition. The determinant of A is equal to the first entry in the first row. Focus on the first row. 1 times the determinant of the matrix. Eliminate the first row and the first column. What is left? 2 3 6 4. Minus second element 0. I know the result of this is going to be 0, but anyway, I'm going to put it so because this is the first time I'm computing this here. So this element is in the position row 1 column 2. So eliminate row 1 column 2. What matrix is left? 5 3 negative 2 and 4. Plus next number, negative 1, plus negative 1 times this entry is in the position row 1 column 1. So what is left? 5 2 negative 2 6. And then we have to do the multiplication. We have to do these computations. Notice how the determinant for a matrix with size 3 by 3 is defined in terms of determinants for a matrix with size 2 by 2. And we already know how to compute this. So in this case, we would have to compute at most 1, 2, 3 determinants with size 3 by 3. I mean 2 by 2. So what it is? Notice this is 1 times this is going to be left only the determinant. So we have equal to 2 times 4 minus 6 times 3. Minus, notice, whatever the determinant is times 0 is going to be 0, right? Minus 0 plus, I think I can here, positive times negative is negative. So we have minus the determinant, 5 times 6 minus negative 2 times 2. And this is equal to what? 8 minus 18 minus 0. Well, I mean, I don't have to write this again, right? Minus 5 times 6, 30. Be careful here. It's going to be negative times negative positive plus 4. And we have negative 8 minus 18, negative 10 minus 34. And we have negative 44. You see? Now, of course, this is the way of computing a determinant for a matrix with size 3 by 3. I know that maybe some of you already know other methods. Maybe for you they were better to compute the determinant. No, again, no problem with that. If you are used to those methods, no problem. But here I'm following the definition. The definition by now is this one. So the answer is negative 44. As long as you get the right answer with any method that you're using or you want to use, no problem. But of course, here we are, this is an online class, so we can take advantage of technology to verify our results or to compute the determinants. So I'm going to recommend one web page to compute the determinant. So let's see. This is a matrix. What? Oh, well, if you go to Google and you write calculator of matrices of determinants, yeah, you see, this is the first page I found, and I think it's okay. So here you have to specify the size of the matrix. Let's verify our result. This matrix has size 3 by 3, so we set the matrix, and then I have to put the entries 1, 0, -1, 5, 2, 3, -2, 6, 4. And then calculate. And notice, you will have the answer, -44. That is the same answer we got, right? -44. So it's correct. So you can use this. You can use this, of course, to verify your computations. Yeah, well, I mean, this is an online class, so I don't see any problem to use this. But of course, you have to verify that you understand how to compute this by hand. Okay. All right. Now, our purpose is going to be to define how to compute the determinant for a matrix with any size. Of course, I'm talking about a square matrix. So for this, we need two concepts. The first concept is the concept of minor. If we have a matrix of size n by n, then the minor if we have a matrix with size n by n, then the minor matrix of A is the n minus 1 times n minus 1 size matrix MRS obtained from removing the rth row and the S column. So yeah, we have a matrix with size n by n, then the minor is a matrix. Minor matrix of A is a matrix with size n minus 1 times n minus 1, so one unit less than the original. That denoted in this way. Be careful, of course. This here doesn't say Mrs. He says these are subscript MRS obtained from removing the rth row and the S column. RS. Yeah. So the subscripts, they indicate their numbers. They indicate what are the columns that we have to remove to get the minor. Example. Given the matrix A, given this matrix A, find our A, the minor 1, 1. So first, this matrix has size 4 by 4. I have to compute the minor 1, 1. So what is the meaning for that? From this matrix A with size 4 by 4, I have to remove or eliminate the row 1 and the column 1. Again, the first number makes reference to the row and the second one to the column. So I have to remove the row 1 and the column 1. I mean, I have to consider the matrix that is left after I have removed the row 1 and column 1. And it's going to be that matrix, negative 2, 3, 0, 7, 6, 5, 1, 0, 3. So M11 is equal to the matrix negative 2, 3, 0, 7, 6, 5, 1, 0, 3. You see? And notice how the size for the resulting matrix, the minor, is 3 by 3. 3 by 3, 4 by 4. You see? It's always one unit less. Now, what about B? M21. M21, I have to what? I have to remove or eliminate from the matrix A the row 2 and the column 1. Row 2 and column 1. What is left? 3, 2, 1. Row 2, column 1, 7, 6, 5, 1, 0, 3. Okay? And so on. For example, what is M12? They are not going to be necessarily the same in general. They are not. But here I have to eliminate what? The row 1 and the column 2. Row 1, column 2. Row 1, column 2. What is left? 5, 3, 0. 8, 6, 5. 2, 0, 3. And again, notice how the sizes for these matrices, they are 3 by 3. So a minor is a matrix. Now, other concept, cofactor. Given a matrix A with size n by n, the cofactor aij, these are subscripts, is defined as aij equal to -1 raised to the sum of the subscripts times the determinant of the minor ij. Note, the number -1 raised to the ai plus j only has two possibilities. Can be 1 if I plus j is even, or can be -1 if I plus j is odd. Only two possibilities. So in other words, the cofactor is -1 raised to the I plus j times the determinant of the minor MIA. Example. Given A equal to 1, 0, -1, 5 through 3, -2, 6, 4. Let's find the cofactor A11. Again, the subscripts, they indicate, they may reference the first number, makes reference to the row, and the second one to the column. So A11. So I have to compute the cofactor A11. And how do I compute this? Follow the definition. Notice, this is a definition that at the same time is a formula. So follow this formula. So in this case, it's going to be -1 raised to the 1 plus 1 times the determinant of the minor 1, 1. In other words, this is going to be -1 raised to the square times the determinant of the minor 1, 1. Remember, the minor is other matrix obtained from this one. I have to eliminate the row 1 and the column 1. Row 1, column 1. What is left? 2, 3, 6, 4. You see? And this is what? Notice, -1 raised to the square, since 2 is 7, -1 raised to the square, -1 raised to the square is going to be only 1. 1 times this determinant is going to be only this determinant. So we have only the determinant 2, 3, 6, and 4. And this is the determinant with size 2 by 2. This is 2 times 4, 8, minus 18. And this is -10. Two times 4 is 8, minus 6 times 3, that is 18. 8 minus 18 is -10. So this is the cofactor A11. What about the cofactor A12? Again, follow the formula. The formula is aia is -1 raised to the sum of the subscripts, -1 raised to the 1 plus 2 times the determinant of the minor 1, 2. -1 raised to the 3 times the determinant of the matrix. I have to eliminate from this matrix the row 1 and the column 2. Row 1, column 2. what is left? 5, 3, negative 2, 4. 5, 3, negative 2, 4. And then negative 1 raised to the 3, since 3 is odd, then we have negative 1 times the determinant of 5 times 4 is 20 minus negative 2 times 3, negative 6. So this becomes negative 20 plus 6. So we have negative 26. And this is the determinant. This is the cofactor A12. And so on. So you pay attention to this. How many cofactors can we have from a given matrix? As many as we have what? As we have entries. So in this case, we have this is a matrix with size 3 by 3. Then we will have 9 elements. We have 9 entries. So we could have 9 cofactors. All right. So once we have understood the concept of minor and cofactor, now we can define how to compute the determinant for a matrix with any size. Determinant of a matrix with size n by n. And the definition is, let A be a matrix with size n by n. We define the determinant of A equal to the element in the row 1, column 1, A11, times the cofactor A11, plus the element in the row 1, column 2, times the cofactor A12, and so on. A1n times the cofactor A1n. Or if you want to use sigma notation, this is the same as the sum from 1 up to n of A1j times the cofactor A1j. This is j. So in other words, computing the determinant implies a sum of the elements of the row 1 times the corresponding cofactors. Let's see one example. Example. Find the determinant of the matrix 1, 2, negative 1, 1, negative 1, 0, 2, negative 2, 3, negative 1, 1, 1, 2, 0, negative 1, and 2. Notice how this is a matrix with size 4 by 4. So pay attention as to how to do it. The determinant of A is going to be equal to, focus on the first row. The first row, the first element. The first element is 1. So I'm going to write 1 times the cofactor A11 plus second element in the row 1, that is 2, times the cofactor A12. Why A12? Because this number 2 is located in the row 1, column 2, plus -1 times A13 plus 1 times A14. This is in the position row 1, column 3, row 1, column 4. You see? -1, 1. And of course, this is going to be simplified to only the cofactor A11 plus twice the cofactor A12 minus the cofactor A13 plus the cofactor A14. So this process, or another way to denote this when you're computing the determinant, is expanding by cofactors in the row 1. Expanding by cofactors in row 1. So this is what we're doing. We are computing the determinant by expanding by cofactors in row 1, in the row 1. You see? Now, what it is, of course, I have to compute it. Let me continue here. This is going to be, remember, A11 is what? Is the cofactor. We have the definition for the cofactor. The cofactor is this is the definition. A11 is going to be -1 raised to the 1 plus 1 times the determinant of the minor 1, 1. The minor 1, 1 is, I have to eliminate row 1, column 1. So it's going to be 0, 2, -2, 0, 2, -2, -1, 1, 1, 0, -1, and 2. Plus twice plus twice times -1 raised to the 1 plus 2 times the minor 1, 2. Eliminate row 1, column 2. Row 1, column 2. -1, 2, -2. 3, 1, 1. 2, -2, 1. -1, 2. Minus -1 raised to the 1 plus 3 times the determinant of the minor 1, 3. Remove the row 1, column 3. -1, 0, -2. -1, 0, -2. 3, -1, 1. And 2, 0, 2. Plus -1 raised to the 1 plus 4 times the determinant of the minor 1, 4. Remove row 1, column 4. -1, 0, 2. 3, -1, 1. 2, 0, -1. And notice, maybe you have realized that we have to do many computations, right, to compute the determinants, and this is only the determinant with the size 4 by 4. Think about this. Try to make the computations and try to get a formula for this. I mean, for if you're going to do this by hand, everything is going to be reduced to compute determinants with size 2 by 2. But we saw before that to compute a determinant with size 2 by 2, we had to compute at most 3 determinants with size 2 by 2. So for each determinant of size 3 by 3, we have at most 3 determinants with size 2 by 2. So 3 times 1, 2, 3, 4. So 4 times 3 would be 12 determinants with size 2 by 2 for a mate at most. 12 determinants with size 2 by 2 for a matrix with size 4 by 4. Imagine if this were with size 5 by 5 and we have to do this by hand, will be 5 times 12 will be 60, and so on, right? So try to get a formula to know that, to compute how many determinants with size 2 by 2 we would have to compute at most to compute the determinant for a matrix with size n by n. But well, by now I have to compute the determinant, right? But I'm going to get help from the web. Is that okay? But first, let me simplify this. This is no. I think I can get I can get the answer. So the first one is determinant 3 by 3 set matrix. The first matrix is 0, 2, negative 2, 0, 2, negative 2, negative 1, 1, 1, 0, negative 1, 2. 0, 2, negative 2, negative 1, 1, 1, 0, negative 1, 0, 2, negative 2, negative 1, 1, 1, 0, negative 1, 2. Calculate. The answer is 2. So this is equal to, notice, I'm here, negative 1 raised to the 2 is going to be 1 times 2, so this is going to be 2. This one, notice, is negative 1 raised to the 3 is going to be negative, so minus 2 times this determinant. So I have to compute it here. I'm going to get help from this web page, 3 by 3, negative 1, 2, negative 1, 2, negative 2, 3, 1, 1, 2, negative 1, 2. Calculate. And the answer is negative 1 for this one, negative 1. So let's see, minus 2 times negative 1. And then minus, notice, this is negative 1 raised to the 1 plus 3 is negative 1 raised to the 4, so it's going to be 1, so minus the determinant. Let's compute it. Negative 1, 0, negative 2. 3, negative 1, 1. 202. We calculate -1, 0, -2, 3, -1, 1, 202. Calculate this. -2. -2 minus -2. And notice plus -1 raised to the 1 plus 4 is -1 to the 5 is odd, so it's going to be minus the determinant. -1, 0, 2. -1, 0, 2, 3, -1, 1. 2, 0, -1. Calculate. It's 3. 3 minus 3. And then I have to do these computations. We have 2 plus 2 plus 2 minus 3. And this becomes 6 minus 3 is equal to 3. So this is the value for the determinant. Determinant is equal to 3, you see? Yeah, if I had to do this by hand, I would have to compute the determinant, the determinant, the determinant, the determinant. See that? And actually, we can verify our solution. Notice, I'm going to introduce now the whole matrix, and we are supposed to obtain 3, right, to verify this result. So let's do it. Now I need a matrix with size 4 by 4. So matrix dimension 4. Set matrix. We have 1, 2, -1, 1, 1, 2, -1, and 1. -1, 0, 0, 2, and -2. 3, -1, 1, and 1. 2, 0, -1, and 2. So notice, I'm supposed to get 3 here, right? And yeah, we got 3. See, so yeah, I know. You can try maybe all the exercises by using this, yeah. But well, it's an online course, so please try to understand how to do it. I recommend to use this calculator or any other a similar calculator that you find to verify, please, to verify answers. Well, so 3. All right. Now, once we have understood how to compute determinants, now let's see some properties for determinants. Some important properties. You know, the computations to compute determinants, you have seen that maybe can be very, very tedious, right? You do it if you are doing this by hand. But actually, I think even a computer or this web page, I don't know how big can I set my matrix. But when you have very, very, very big matrix, maybe the computations can be a lot. That's why we can take advantage of properties for determinants. So here, some properties. Of determinants. Number 1, determinant of the product of two matrices is the same as the determinant of A times the determinant of B. The determinant of a product of two matrices is the product of the determinants. Be careful. Note, in general, the determinant of A plus B is not the same as the determinant of A plus the determinant of B. So don't try to follow that rule. This rule is not true. If you have a sum of two matrices and you want to compute the determinant for that, it's not the sum of the corresponding determinants. But when we have a product or multiplication, it is true. Let's see one quick example. If A is equal to 1, 0, 2, 1, and B is equal to 1, negative 1, 1 and 1, then notice the determinant of A is what? Is 1 times 1 is 1 minus 0, that is only 1. And the determinant of B is 1 times negative 1, 1 times negative 1, minus 1 times 1. So it's negative 1 minus 1, that is negative 2. So let's find the multiplication of these two matrices. A times B is equal to 1, 0, 2, 1 times 1, 1, 1, negative 1. And this is going to be row 1, column 1. 1 times 1 is 1, plus 0 times 1, we have 1. Row 1, column 2, row 1, column 2, 1 times 1, 1, plus 0 times negative 1 is 1. Row 2, column 1, row 2, column 1, 2 times 1, 2, plus 1 times 1 is 3. And here, row 2, column 2, this times this, 2 times 1 is 2, times the 1 times negative plus 1 times negative 1 is 2 minus 1 is 1. Now, notice the determinant of this matrix AB is equal to 1 minus 3, that is negative 2. And the determinant of A times the determinant of B is equal to 1 times negative 2, that in this case is negative 2. So, of course, the determinant of AB is the same as the determinant of A times the determinant of B. So this is a good property that maybe for some, when we have to do some computations, we can use this property, right? In the exercises, I think we have to use this property for some of the exercises. All right, so this is the property number 1. Property number 1. Number 2. If you have a matrix with size n by n, then the determinant of A is equal to yeah, I know. It seems like I'm using the same definition for determinants that I have used before, but no, not exactly. In the previous definition, notice the first was the number one, and this means expanding by cofactors, as I said here, expanding by cofactors in row one. Here, the first number in the subscript is 1 and 1 here because we are expanding by cofactors in the row 1. But actually, to be honest, it's not necessary to expand by cofactors in row 1. You can do it in any row. If you do it in any row, the answer is going to be exactly the same. In other words, we can expand by cofactors in any row to compute the determinant. Example. Let's see the first example for the matrix. This matrix. 1, 0, -1, 5, 2, 3, 1, 0, -1, 5, 2, 3, -2, 6, 4. Let me verify because 1, 0, -1, 5, 2, 3, -2, 6, 4. Yeah, it's correct. Well, I'm sorry. We saw before that this. Oh no! Wait a minute. We didn't compute the determinant for this one, right? I'm sorry. I'm sorry. Oh yeah, -44. Yeah, I'm sorry. So notice here I expanded by cofactors in the row one. I know we use the definition, but the definition is only the definition expanding by cofactors in row one. But now I'm going to expand by cofactors in row two, and you will see the answer is going to be the same. We will expand by cofactors in row 2. So the determinant of A is going to be focus on the row 2. 5 times the cofactor 2, 1 plus 2 times the cofactor A22 because this 2 is in the row 2, column 2. This one, row 1, row 2, column 3 plus 3 times A23. And this is equal to 5 times -1 raised to the 2 plus 1 times the minor 2, 1. Minor 2, 1, remove the row 2, column 1, 0, -1, 6, 4. plus 2 times the cofactor to 2, negative 1 raised to the 2 plus 2 times remove row 2, column 2. Row 2, column 2. 1, negative 1, negative 2, 4. 1, negative 1, negative 2, 4. Plus 3 times negative 1 raised to the 2 plus 3. I'm using the definition for cofactor, that okay? Times the minor 2, 3. Remove row 2, column 3. 1, 0, negative 2, 6. And this is going to be what? 5, negative 1 raised to the 2 plus 1 is negative 1 times the determinant. 0 times 4 is 0, minus 6 times negative 1 is 6. Plus, notice here, this is going to be 1, so 2 times the determinant. 1 times 4 is 4, minus negative 2 times negative 1 is 2, plus 3 times negative, this is going to be negative 1 raised to 2 plus 3, negative 1 raised to 5, so it's going to be negative 1 times 1 times 6 is 6, minus 2 times 0, minus 0. And this becomes negative 30. 5 times negative 1, negative 5 times 6, negative 30. 4 times negative 2 is 2. 2 times 2 is 4. Plus 4 minus 18. And we have negative 48 plus 4, and this is equal to negative 44. So the answer is exactly the same, you see, as the one we obtained before. In the very first, yeah, this one. But here we expanded by cofactors in the row 1, and here we did it in the row 2. So the answer is the same. So no matter where you expand by cofactors, the answer is going to be the same. Yeah. So in that case, it's recommendable that you use a row that you expand by cofactors in a row that you think the computations are going to be simpler, right? All right. Three. If we have a matrix is a triangular matrix, then the determinant of A is only the product of the elements in the diagonal, in the main diagonal. Triangular matrices are the ones, for example, this one, 1, 2, 3, 0, 5, 6, 0, 0, and 7. I mean, those are matrices where either above triangular matrices are those where below the main diagonal, in this case this one, we have only zeros, or can be above. For example, other example of a matrix like this is going to be 1, 2, 3, 4. Again, notice below the main diagonal, only zeros. Other case could be 1, -2, 2, 5, 6, 3, and then 0, 0, 0. You see? In this case, this is the main diagonal. Above the main diagonal, we have only zeros. So either above or below the main diagonal, we have only zeros. That is a triangular matrix. When we have a matrix like this, the determinant is only the product of the numbers in the main diagonal. For example, for this one, determinant, let me call this A, is only the product of 1 times 2 times 3. It's only 6. You see? So when you have a matrix like this, the computations are, I think they are very simple, right? Only multiply the elements in the main diagonal. Number 4, the determinant of A is the same as the determinant of the transpose. So remember that the transpose is when we get the matrix, when we create the matrix from A by putting the rows as columns. So the determinant for that is exactly the same for A and for its transpose. So this means as a corollary, the determinant can be computed expanding by cofactors in rows or columns. So in this example, I expanded by cofactors in the row 2. But if I want to expand by cofactors in the column 1 or the column 2 or the column 3 by following this process, the answer is going to be exactly the same. So you can expand by cofactors in either row 1, row 2, row 3, or column 1, column 2, and column 3. The answer is going to be the same. Yeah. Number 5. So this property says if you have a matrix A and you create a matrix B by interchanging the order of two rows or two columns because of the property number 4, by interchanging the order of two rows in A, then the determinant of that new matrix is the same determinant as before of the matrix A, but put a negative sign. For example, for this matrix 1 0 negative 1, 5 2 3, negative 2 6 4, the determinant of A is equal to negative 44. Yeah, we computed this before, and we computed this by in two ways, and we verified this in the calculator. So now notice I'm going to create the matrix B. It's going to be based on this matrix A, but I'm going to interchange or to change the row 1 by the row 3, I mean the position. So I put the row 3 at the row 1, negative 2 6 4. Row 2 as it is, 5 2 3, and row 3, row 1, 1 0 negative 1. So you see this matrix is the same as this one, but only difference is that I interchanged this row by this row, the order, row 1 by row 3. Okay, so then the determinant of B is going to be negative times the determinant of A. And the determinant of A we know is negative 44. So in this case, the determinant is going to be 44. That is the property number 5. Number 6. If A is of size n by n and has two identical rows or columns, then the determinant of A is automatically 0. If you see a matrix with two rows or two columns exactly the same, do not waste time. Let's say I have 1 2 3 4 0 negative 1 0 2 3 4 7 8 and 1 2 3 4. Yeah, notice this row and this row, they are the same. If you see two rows equal or two columns equal, automatically then the determinant of A is 0. just like that. This row is the same as this row, so automatically determinant is 0, no matter how big is the matrix is. Okay, 60 by 60, 40 by 40, no matter the size. You see two rows or two columns equal, determinant is 0 automatically. Number 7. Suppose B is obtained Property number 7. Suppose B is obtained from A by multiplying one row or column of A by a non-zero constant C. Then the effect that has on the new matrix, well, on the previous matrix, is the determinant multiplied times C. Be careful. This is not saying that you have to multiply all the whole elements in the matrix. So I mean all the whole matrix, all the elements in the matrix. No. Only one row or one column. Example. We know that if A is equal to 1, 0, negative 1, 5, 2, 3, negative 2, 6, 4, then the determinant is negative 44. I mean, negative 44. We have verified this several times before. Negative 44. So I'm going to create a matrix B that is going to be the same as the matrix A, 1, 0, negative 1. But now I'm going to multiply the row 2 by 2. So it's going to be 2 times 5, 2 times 2, and 2 times 3. The rest the same. I want you to see and multiply times 2, times 2, times 2. And this is 1, 0, negative 1, 10, 4, 6, negative 2, 6, 4. Then the determinant of B is going to be 2 times determinant of A, or 2 times negative 44. This is negative 88. You see, if you multiply the effect that has on the determinant to multiply one row or one column times a constant is multiply the determinant times that constant. Okay, again, only one row or only one column, not the whole matrix. So this property maybe is going to be confusing at first glance, but this is very useful. Let's say that we have a matrix A, and suppose that B is obtained from A by replacing the ith row, for example, the first one, the second one, the third one of A, by that row plus other row, here identify as kth, but multiply times a constant. Then if you do that, the determinant doesn't change. Example. Given the matrix A 1 2 1 0 3 2 -2 1 1, and let's say that you want to compute the determinant for this matrix by hand, but you say, oh, how can I simplify this to make the computation simpler? Well, we can take advantage of the property number 8. Notice what I'm going to do is I'm going to add the row 3 plus twice the row 1. And then I'm going to put that in the row 3. This is the property number 8. In this case, the ith row is the row 3. I am adding to the row 3 other row, in this case, the kth row, in this case, the row 1, times a constant. You see? Row 3 plus twice other row, a constant. And this result, I'm using this result to change the first row, row 3. If we do this operation on the matrix, the determinant should be the same according to this property. So let's do it. I will have, notice, I'm going to change only the row 3. So row 1 is the same, and row 2 is the same. Now row 3. 2 times row 1, 2 times 2 is 2. 2 plus -2 is 0. Yeah, now you see why I chose these numbers 2, or the number 2, to have here 0. 2 times 1, 2 times 2, 2 times row 1, 2 times 2, 4, plus 1, 5. And 2 times 1, 2, plus 1, 3. And notice, now I have this column with 2 zeros, so I can expand by cofactors in the column 1 to compute the determinant of B. We will expand by cofactors in column 1. So this is going to be the determinant of A is going to be 1. This 1 is in the position row 1, column 1. 1 times the cofactor 1, 1, plus 0 times, what is this 0? Row 2, column 1. plus the 0 times row 3, column 1. You see, I expanded by cofactors in the row 1. This determinant, the determinant can be computed again, expanding by cofactors in any row or in any column, and the answer is going to be the same. So here we have only this is going to be only 1 times A11, 1 times A11, so it's going to be only the cofactor 11, A11. And this is negative 1 raised to the 1 plus 1 times the determinant of the matrix of the minor 1, 1. Eliminate the row 1 and column 1 here in this matrix, yeah? Oh, I'm sorry. Maybe, yeah, I mean, the answer is going to be the same, but I'm sorry. We're supposed to be computing this on B, but yeah, it's going to be the same as A, but formally I'm using B here. So we're working with this matrix. So the minor 1, 1, eliminate row 1, column 1. 3, 2, 5, 3. 3, 2, 5, 3. And this is going to be only 1, so it's going to be only the determinant. 3 times 3, 9, minus 5 times 2 is 10, is negative 1. So the determinant of B is supposed to be negative 1. And according to the property number 8, this operation we did here doesn't change the determinant of A. So the determinant of B should be the same determinant of A. We can compute it by hand, or we can use the calculator to verify that. So once more, let me use this calculator. Dimension 3 by 3. Set the matrix. The entries, I'm going to use the matrix A, okay? 1, 2, 1. 0, 3, 2. Negative 2, 1, and 1. Calculate. What is the answer? Negative 1. So the same answer we got here. Negative 1. You see? So this property might be very useful, right? Because it's like you can try to take advantage of this property to make zeros, and if you can make zeros, the computation of the determinant can be simpler. All right, that's all by now. If you have any question, remember you can use you can let me know. You can send me your questions. See you in the next video.